Thank you, Adam, and thanks for the invitation. So from my sort of slightly biased perspective, modern NLP typically is a combination of two ingredients. The first is a representation, which typically is at least 50 years old. So finite automata go back to the 40s. The other major representations that are used were developed in the 50s. And these representations then are combined with contemporary machine learning techniques. So, you know, max margin approaches, deep belief networks, whatever the current set of techniques are that people are using. And these two ingredients are then combined to produce an NLP system. Now, in cartoon form, I guess, we can look at it something like this, that we combine some old vehicle, we stick a modern engine on it, and we end up with something like this, right? Which, of course, is really, really awesome, and it goes very, very fast, right? But, you know, maybe we can do better, right? Maybe actually there are better things that we could strap our machine learning techniques onto that might go even faster than this. So this talk is, for NLP people, going to be a bit weird and old-fashioned. And in a way it is old-fashioned because some of the research I'm doing is describing is essentially redoing some of this 1960s work. And in a sense, I think some of this work should have been done in the 1970s. Okay, so what I'm really trying to do is to re-examine one or two fundamental assumptions that were made in the 1960s about syntactic structure in particular, and see maybe whether we can turn a really ill-posed and intractably hard problem into something that we can actually solve. Now, when you think about regular languages and automata theory, I have absolutely no corrections to make to this theory at all. I think it's really quite complete. We have all that classical automata and transducer theory, the Kleene theorem, the Myhill-Nerode theorem, the Eilenberg cross-section theorem. We have canonical representations for regular languages. And these read into algorithms like Dana Anglin's classic learnability results. We have determinization and minimization algorithms. And we have these wonderful finite state transducer and weighted finite state transducer algorithms that are used very extensively in NLP. So at this level, this is great. Everything's fine. But of course, natural languages are really not regular, right? So we need to consider richer and more powerful representations. And in particular, I'm going to be looking at context-free grammars and context-free languages. And at this level, there is, for me at least, a really big problem. And that is the idea that a syntactic structure can be viewed in some sense as a derivation tree of a context-free grammar. Now, if we have a context-free grammar, one thing we might want to do is learn this from strings. So we're given a sequence of strings, and we want to learn a grammar that generates the right set of strings, that generates these strings, and also some appropriate, you know, superset of them will generalize normally to some infinite set. Or we might want to pick a PCFG that has low divergence from some target distribution. So that's a perfectly good, well-defined task. It's pretty hard, but you know, we have some algorithms that can do that. What we don't have really is the same set of algorithms for strong learning of context-free grammars, which is we can think of as being unsupervised parsing. So this is here where we're given a set of flat strings, so strings that aren't annotated with their syntactic structures, so not a tree bank here, just flat strings. And we want to find some grammar G that generates kind of the right tree structures, or a PCFG that generates the right conditional structure, conditional distribution of trees given these yields. And this is clearly a hopelessly ill-posed problem, right? Because there are many different context-free grammars that will generate the same set of strings. And even when we move to a PCFG-based thing, there are many different PCFGs that will generate the same distribution. So in stochastic terms, they're not identifiable. So in order to answer this question, we need to think a little bit about some sort of fundamental methodological questions like, so what is syntactic structure? You know, these parse trees that we have in tree banks, these lexical categories. And a sort of very naive view is that this is data, right? That, you know, we're computer scientists, and the linguists are the scientists, and they have their data. They've run some experiments, and they've got this data out from their microscopes or whatever it is, and they annotate this helpfully for us. And so this is some data that we should model as computer scientists. Now, this, of course, is not at all what the situation is. You know, these annotations are theory. They're not data, right? They're theoretical predictions that linguists, syntacticians have come up with to model the relationship between the sequence of words and the meanings. And linguists really don't know what the syntactic structure is, and they can't agree about it at all, right? So this is a fairly blunt quote by Jim Blevins, who's a linguist at Cambridge, Cambridge, UK. At the most fundamental level, it's not clear there's any meaningful empirical motivation for the representation assumptions of any current formal model of syntax. Okay, so that's pretty tough. But just on a detailed level, you know, linguists can't agree whether the head of a noun phrase like the cat is the or cat, and they don't have any empirical evidence to decide between the two. And Jeff Pullum has his example is show me the money, right? That if you ask 10 different linguists to annotate show me the money, you'll get, you know, well, as the old joke has it, you'll get 11 different parse trees, right? Now, if we just zoom out a little bit to sort of theoretical linguistics, this is a quote by Norbert Hornstein saying that for a very, very long time now, well, basically, you can read the quote, but basically Chomsky's view, and I kind of agree with Chomsky on this point at least, that what you're studying at in linguistics is not really the structures of individual languages. What you're interested in is the powers that enable human beings, children, to acquire these languages, right? Now, I completely agree with this, the first thing, and of course, you know, what linguists actually do, since most of them aren't interested in learning or grammatical inferences, they construct descriptive grammars of languages. Now, the standard view that if you've taken Linguistics 101, you probably saw something like this. The idea is that what linguists do is we have the input, which is some set of strings. Then we have a language acquisition device, which is some cognitively realized learning algorithm in the child's brain. And this produces some output, which will be a grammar. Okay? So we're just thinking about context-free grammars at the moment. So you're going to have a set of strings. We have some inference algorithm. And then we have a context-free grammar that comes out. So the idea for the way that linguistics should proceed, right, is that first of all, we figure out what this is, right? We figure out the I language, right? Then we know what the input is because we can observe it. And then once we've got the input and the output, right, then we can figure out what's going on in this box. Okay, so that seems like a perfectly reasonable way to proceed. But the diagram conceals something, which is that we don't observe the I language, right? We don't observe the grammar. What we observe is what linguists call E language, which is a sort of the set of pairs of surface strings and meanings, right? And we don't observe either the language acquisition device or this internal grammar. So we don't know what the internal grammar is. And Chomsky kind of recognized this pretty early on. The choice of a descriptively adequate grammar, so that means, you know, grammar that defines the right set of trees, is always underdetermined by the language. Okay, so this maybe is a better diagram here, that we have several different possible theories, right? Several different possible grammars, right, that are going to explain the same data, the same information. So we have, if you like, three different extensionally equivalent grammars that generate the same set of strings. So how can we figure out which is the right one? Well, in principle, really, what this diagram shows is that the right answer is going to be something that is the output of a learning algorithm, right? That we can, if we consider, we need to consider not just the fact that these languages generate the set of strings, but also the fact that we know they can be learned. That is the output of a learning algorithm. And if we add that constraint, then this is going to narrow down the set of structures that we need. And so these structures then, it's kind of uncontroversial that these structural descriptions, these parse trees, are only really significant as long as to do this, mediate this relationship between prosody, between the sequence of sounds that we hear and the semantic properties. Okay? The syntactic structure itself is not really predictive. And one might feel that there's sort of psycholinguistic data that could help you. For example, that we might have data from psycholinguistic experiments or from neural imaging experiments. So there's quite a long history of this data. But this data doesn't really tell you exactly what sort of structures we've got. It tells you that there are certain similarities between structures, particularly the structural priming literature is very interesting, but it doesn't tell you exactly what these structures are. So in summary, right, linguists and psycholinguists and neuroscientists aren't really going to help here, right? And the reason they're not going to be a help is that the central problem, for me at least, from my perspective, is a problem with context-free grammars. It's a computational problem. And that is the problem, that the class of context-free grammars is way too large. It's also, I think, slightly too small, in the sense it's not rich enough to deal with various movement phenomena, but it's too large in the sense that for any language, we have infinitely many context-free grammars that are going to generate that language. These can assign arbitrary structures to any finite subset of strings, right? So the thing is that if we're using context-free grammars, the whole class of context-free grammars as the representations, the problem of recovering the syntactic structure is ill-posed. There are too many possibilities. So we need to find some theoretically motivated way of modifying context-free grammars, restricting them in some way, to give a well-defined notion of syntactic structure that can be learned. Okay? So the crucial point is we want to modify context-free grammars so we end up with some syntactic structure that we can learn. And also that will, in some sense, be correlated with the properties of syntactic structure that we want.
Can I interrupt?
Yeah, of course, of course.
So the we need in the last bullet seems a little strong because it seems like it would exclude Bayesian approaches, which say, well, we don't have a theoretically motivated way of narrowing down which CFG we want. We just have an empirical observation that people seem to have an inductive bias of a particular kind. We're going to empirically write down what that inductive bias is. It doesn't give us a well-defined notion of a restricted class of CFGs.
Yeah, well, actually, part of my talk is that in a sense, it does. So I'll come back to that. In fact, there's a Bayesian slide coming up in about 3 or 4 slides. But yes, I guess maybe it's too. That's just when it means maybe I should replace that with I. Okay, so I'm going to do some slightly unfamiliar algebra later on. So I'll start with some kind of familiar sort of things. So in a standard machine learning problem here, we want to learn some function from a space X to a space Y from a sequence of input-output pairs. And we want our hypothesis to tend to the right answer as the data increases. Now, obviously, if you've just got spaces X and Y, there's nothing you can do, right? You can only do some learning when you assume that these spaces have some sort of algebraic structure. So you have to make an assumption that they have some algebraic structure, and people often assume it's essentially a vector space. And then in addition, you assume that the things you're learning are well behaved with respect to that algebraic structure. So you might assume maybe that f is linear, or it satisfies some kind of smoothness condition like that. And if we have these two things, then we can do some learning. Okay. Now, the other thing that we often do is, and this is kind of linear algebra 101, I assume you're all very familiar with this, is we define, maybe a linear map. We want to reduce the dimensionality of our space by mapping it from some high-dimensional space n to some low-dimensional space k. And that's how we would define linearity. So zooming out a little bit, a linear map is just a homomorphism of the vector space, and the homomorphism is going to define a congruence relation between elements of the original space, where we say that x and y are similar to each other if there are differences in the kernel of f. So what we're saying here really is that we have this high-dimensional space. In some dimensions, we're interested in some dimensions, and we're not interested in other dimensions, so we're going to map it to a smaller space that collapses the uninteresting dimensions to a point. Okay? And then we have one of the standard isomorphism theorems that we can take the quotient of this vector space by this congruence, and that's going to be isomorphic to the image of the thing, which is one of Emmy Noether's isomorphism theorems. Now, if k is too small, you're going to lose information, right? So if you map it down just to one dimension and the data is actually underlyingly three-dimensional, then things are going to go wrong. So you want to map it down as much as possible, but not too much. Okay? So I assume this is all very familiar. Now, in computational linguistics and NLP and linguistics, indeed, we're interested not with real vector spaces, but with discrete combinatorial structures, right, with strings or trees or labeled sequences. And one way of dealing with this is just to ignore this mismatch and say, well, we have this beautiful theory of learning in real vector spaces, so what we're going to do is we're just going to use that theory, we're going to map everything into a vector space, we're going to do our stuff in this vector space, apply our wonderful algorithms, and then we're going to map it back. And this works really well. But I'm going to try a different strategy, which is that we say, okay, well, we're not dealing with vector spaces here. We're dealing with discrete combinatorial structures. Maybe they're not necessarily noisy. And we have these strings, trees, and grass, and we can combine them with some operation that takes two small objects and makes a bigger object. So there are sort of two spaces we might be interested in. One is just the set of all strings, which we write sigma star. But I think it's important actually here to lift from that to sets of strings, so we're going to consider the power set of all strings. So the structure, our input space, if you like, is going to consist of sets of strings. So this is a set of all infinite or finite sets of strings. Now, one of the ways we can use this structure is to interpret context-free grammars. So we tend to think of context-free grammars in one of two different ways, either as a machine model using a push-down automaton, or as a rewriting system, or as a system of well-formedness on trees. There's another way, which is due to Ginsburg and Rice, where you have a sort of equational semantics for it, where we interpret each non-terminal as being a set of strings. So we're going to map from, we can do as a function from the non-terminals of our context-free grammar into this collection of all sets of strings, where we're going to map each non-terminal just to the set of strings that are generated by that non-terminal. And in particular, S, our start symbol, is going to be mapped into the language. Okay. So I'm just to clarify, I'm dealing here in a non-probabilistic case because I'm still stuck in the 1970s. Of course, in the current day, I do realize that probabilities are, I don't have any prejudice against probabilities. It's just the maths is a little easier without it at the moment. Now, what Ginsburg and Rice show is that if you have some context-free grammar, maybe which just has this set of productions here, we can view this as a set of equations, right, where we take the S now, instead of being a symbol, is a variable that refers to a set of strings, and we can convert each of these, the right-hand sides of each of these productions by using this concatenation operation, which is just concatenation of sets of strings, and where we have several different non-terminals, and several different productions with the same left-hand side, we take the union of them. And it's fairly easy to see that if we can convert any context-free grammar with n non-terminals into a set of n equations, and the language generated by it is going to be, in a sense, the smallest solution to this set of equations. Okay, so this is an alternative to the standard ways of viewing context-free grammars, but it's in every way equivalent. Like I say, we're going to be thinking about these. We want to think about these sets of strings. So it's first good just to think about the strings. Well, what are strings? It's we classically talk about it as a free monoid. So it's a free structure over this set with one associative operation and a unit. So it's a semigroup with a unit. We're interested in the power set of this. So this is again a free structure over sigma, but it has one more operation. Instead of just concatenating things, we can also take the union of things. So we have two operations, and the appropriate algebraic structure for this is a type of semiring, which is called a complete idempotent semiring. Okay, so I'll just call it a CIS. It's a semiring, which many of you know from semiring parsing. It's a little bit different because it's complete, which means you can take countable unions because you want to be able to consider infinite sets. And it's idempotent because the x union with x is itself. So we're dealing not with real vector spaces here, but now with these complete idempotent semirings. And the question is, like, well, you know, what are the naturally learnable classes here? What are the linear functions? What are the convex regions? What are the nice learnable things with respect to this slightly weird algebraic structure? Now, this is maybe a slide that goes some way towards helping answer Jason's question. So one way of learning a grammar might be to take some Bayesian or MDL type approach, right? So let's, here we're considering, I'm doing this a little bit informally, so, but let's say we just have an infinite data limit, and we figured out what the grammar is, we figured out what the language is, and what we're interested in is the problem of finding the right grammar for this language. And one natural way of doing this might be to try and find the smallest context-free grammar for every language, right? So the grammar that amongst the set of all grammars that define this language is the smallest one. So there's no particular reason for this to be unique. We might have several ones that have the same thing. And you know, what exactly is our measure of size? What exactly is our prior? So these are all problems one can perhaps deal with. What I want to do is take a different approach, which I'll develop a bit later. Which I hope I'll demonstrate then is pretty much the same as this original approach under some circumstances. So let's assume at the moment that we can do weak learning, right? We'll assume that we have some algorithm that can learn the right set of strings, and now we're interested in the problem of saying, well, what's the right syntactic structure? Okay, so suppose we have some fixed language, right, L star, and we have some grammar here that defines this language. But suppose it's like really, really big. It's redundant. We want to find something that's maybe a bit smaller. So one way of making it smaller is to merge non-terminals, right? So one way you can do this is through a grammar morphism, right? So we're going to have a transformation of a grammar where we just map the non-terminals V here into some other set X. And we just convert the productions in the absolutely standard way. And this is a strong thing in the sense that if we get we have a derivation tree with respect to the original grammar, we'll map it to a derivation tree with respect to our transformed grammar. So pretty obviously the language defined by this transformed grammar is going to be is going to include the original language. So in particular we might have a grammar like this where we just have these 4 non-terminals, okay, and we apply some morphism that merges A and B, and this is going to give us a merged grammar like this, which is going to be a larger set. And we can carry on merging it down until we end up with a grammar with just one non-terminal which generates all odd length strings. Okay, so here what we're doing is we're kind of reducing the grammar. If we reduce it too far, it's going to generate too much. Now, let's say our grammar is really, it's really big. We have two distinct non-terminals that generate exactly the same set of strings, the same sublanguage, right? So we have two non-terminals A and B, such that the set of strings generated by A and the set of strings generated by B are identical. Well, this is clearly a redundancy we want to eliminate in this grammar. So we can merge them. And we can merge them with a map where we map each non-terminal to the set of strings. So what we're doing here is essentially we're considering sets of non-terminals to be sets of strings. So mathematically we map it, each non-terminal, to this infinite set of strings. Okay? We can view this as a map from a context-free grammar into our power set, our complete idempotent semi-ring, right? So what we've done here is we have our grammars, which are kind of hard to deal with and ugly, and we can't compute with them nicely. But we also have our semi-rings, the algebraic structures, which are nice, well-behaved algebraic objects. So by doing this map here, we moved from our grammatical representation to an algebraic representation. Now, I guess this probably isn't going to be a huge surprise, but we're going to do homomorphisms of these algebraic objects, these semi-rings. So a homomorphism is just exactly the same thing as a linear map, except instead of being in a vector space, yes?
Sorry, I missed something. What happens with productions in this mapping CFGs to CIS?
Well, the productions are just mapped in exactly the way you would with if we merge two non-terminals, then we're going.
So you're saying that CIS has productions?
The CIS doesn't have productions now. The grammar has productions. The CIS just has these operations of concatenation and the two primitive operations. So it's a simple algebraic object. But can you wait one slide, because I think it will become clear. So it's this homomorphism is exactly the same. It's just linearity, but instead of being in a vector space, it's in a semi-ring. Now, this is where the payoff comes for all these definitions, right, is that a homomorphism of these semi-rings gives you a morphism of the grammar, right, that we can transform we can take any homomorphism, right, from our free semi-ring into something else, into anything else. If it's a homomorphism, then we're going to get a very nice CFG morphism. And the reason we're going to get a nice CFG morphism is because of the equational semantics, right? Ginsberg and Rice define the meaning of a context-free grammar through these sets of equations. Because it's a homomorphism, if this is true in the original power set, then when we take the homomorphism, it's also going to be true with respect to the it's also going to be true in the transform space, okay, because it's a homomorphism, okay? So this means that instead of trying to do horrible merging in context-free grammars, we can do nice homomorphisms in our semi-rings. Now, there are obviously two extreme cases here. One case is where we just have the identity map, which doesn't change anything. And this is just going to be equivalent to the case where we only merge non-terminals that generate the same language. Okay, that's not very interesting. And then we also have the case where we map everything to just the trivial one element semi-ring, right? And this is going to merge everything into, all non-terminals are going to be merged into the same element. And this is usually going to increase the language generated to sigma star. Right? So if we have a simple homomorphism, we're going to preserve it. If we have a homomorphism which is a bit too aggressive, we're going to end up overgeneralizing. Now, we define the details don't matter, but the equivalent of an inverse. It's, we can't have an exact inverse because, because it's not a bijection, right? So we have it's what's actually called the residual. And then we can say, this definition here, we can say that a semi-ring here recognizes a language if and only if the element that L is mapped to actually corresponds just to L. Okay, so what we're saying here is that we're having a homomorphism of our original free power set semi-ring into something else. We pick the element that corresponds to the language we're interested in. That is going to be mapped to some element in B. And the question is does that correspond to just to L or to some larger set? And this is just an analog of the classic automated theoretic idea of a monoid recognizing a language, which I assume most people aren't that familiar with, but I'm just bringing that out. So now we can say we want to merge as much as possible while still generating the same language. So the idea here is we have some big context-free grammar. We want to merge non-terminals as much as possible while generating the same language. And we can show that this language is going to define the same language, that the merged grammar is going to define the same as the original language, if and only if this lattice, this semi-ring, recognizes L through this morphism. Okay, so that's nice. So we have these homomorphisms which define transformational context-free grammar, and this transformation is not going to increase the grammar if and only if we have this criteria. Now what we can show is that there is a unique answer. Okay, there is a unique smallest semi-ring that recognizes L. And this is going to give us a unique morphism to simplify our grammar. Okay, so let me just do this in a little diagram here. So here we have here the set. We start off here with our semi-rings. Right? This is the original semi-ring, which is a set of all languages. Okay, and over here we have the trivial one element semi-ring. Okay, and we can map. We can have homomorphisms that go from here. Right? Now, what I'm saying is that the set, if you consider the set of all semi-rings that recognize L, they're the ones that are shaded green. Right? And there is a unique smallest one here, in the sense that if there's any other one that recognizes it, we can find a homomorphism from that one to this one, right? So it has there's a sort of category theoretic interpretation which I won't trouble you with. But basically the point is that this is unique for each language. And it's a structure called the syntactic concept lattice, because semi-rings are also, of this type, are also lattices. Now what does this mean in terms of grammars? Well, here if we think of it in terms of grammars, what we have is we have our original grammar up there. We map it to here, and here what we're doing is we're just merging, we're only merging non-terminals that generate exactly the same set of strings. So that's kind of, we obviously want to merge them. But then we can apply this universal morphism, right, that will transform any grammar, essentially map any grammar for this language into the same sort of universal algebraic set. Okay? Right, so this is essentially what we're doing is we're taking the classical automator theory, where we have strings, we're lifting it to sets of strings, and this gives us this universal morphism, which is a universal transformation of context-free grammars. Okay, so every complete idempotent semi-ring is also a residuated lattice, and this smallest lattice for each language is called the syntactic concept lattice. And it is the lattice of all distributionally definable sets of strings with respect to a language. Okay, so one of the points I want to make here is that distributional learning ideas, where we're trying to model the relationship between substrings and contexts and build algorithms based on that, and a sort of simplicity-based learning for context-free, actually converge, in a sense, to not quite the same thing, but to the same set of symbols. So we have a unique smallest semi-ring that recognizes the language. This doesn't mean we have a unique smallest context-free grammar. Ideally, that's what we'd like, right? We'd like to say, okay, for each language here, there's a unique context-free grammar. That would be wonderful. We're not quite there, but we have a unique set of non-terminals that are now not arbitrary symbols, right, but elements of a non-trivial algebraic structure. And that means we have things like partial orders. We have a whole bunch of algebraic structure that we can use to reason with these non-terminals. We can take any non-terminal for the grammar, apply this universal morphism, and we'll get a grammar which is possibly smaller, that uses non-terminals that are these elements of this algebraic structure. So just a trivial example, just to give you a concrete example of what this looks like, if the language is regular, then this semi-ring, this lattice, is going to be finite. So for the trivial regular language A, B star, we end up with this thing which has these 7 sets of strings. So what this means is if you have any context-free grammar that generates this language, we can apply the morphism to it, and we can map each non-terminal to one of these 7 symbols, and we will get a grammar that defines the same language but using these symbols. Okay, so this is the to define the syntactic concept lattice. So now I'm going to define the same structure using distributional terminology. So if we have a set of strings here, S is a set of strings, we can consider the set of contexts, where a context is just an ordered pair of strings, or equivalently a sentence with a gap. We can consider a set of contexts such that all of the elements of S can occur in that context. Okay? So this, in a sense, this says that for a set of strings, this is the distributional property of this set of strings. Okay? Actually, I'm going to skip this. Now, I'm going to skip over a little bit of material here, but one way of defining this structure is saying that we define a congruence here, where we say that 2 sets of strings are equivalent if they have the same, they can occur in the same set of contexts, right? And this is a congruence of the semi-ring, and this lattice is just the quotient of this by this congruence. So just like when you do a dimensionality reduction in a real vector space, you're saying these 2 strings are, the difference between these 2 strings is uninteresting, so we're going to quotient it out. Here what we're saying is we take this distributional equivalence, we quotient that out, and we get this unique sort of low dimensional, if I can abuse notation like that, representation. And crucially, we can just observe this stuff. We can observe the closed sets of strings just by taking data and looking at the relationship between sets of strings and contexts. I must go, let's get this. So what we're going to do is assume now that the non-terminals in our context-free grammars are elements of this lattice. And the question is now, can we define now a notion of structure which is based on this? So we're going to take trees, actually I don't necessarily need this. We're going to take trees of a fairly standard type, okay, where we have a tree domain which defines the structure, and then a mapping from that structure into a set of labels. Okay, so again, we fix a context-free language. We pick any grammar, G, that defines that grammar, that language. And then for a given sentence, we consider every possible parse tree under every possible grammar for that language, and we map it under this universal morphism. Okay, this is going to give us an infinite set of trees that have the following property. The root is going to be labeled with L itself. The frontier is going to give you W. The branch nodes are going to be labeled with closed sets of strings. And at every local tree, we're going to have a monotonicity condition, which is that this W is going to be a superset of the concatenation of the strings that the leaves. Okay, so we're going to have an infinite set of trees like this. And what we want to say now is, well, some of these trees are better than others. Okay? So the first thing we can say is there's going to be a partial order on these trees. Okay, because we have this nice algebraic structure, we have a partial order here. So we fix the structure of the tree, we fix the leaves, and then we have a partial order in the natural way. We're going to say this one is less than this one if this one is less than or equal to this one, and this one is less than or equal to this one, and so on. A natural point-wise partial order.
So this is where the trees have the same structure?
Well,
you mean by fixing the tree domain?
Yeah, exactly. So the trees have the same structure, the same leaves. We have a natural partial order. Okay. Now, if we fix a particular structure, we're going to have a unique minimum element here, but possibly several different maxima. So I'm running out of time a little bit. So the unique minimum labeling isn't very interesting. It's just a smaller set of strings that includes the yield of each subtree. Okay, but the maxima are much more interesting. If we think of a simple case of lexical ambiguity here, where we have maybe a word like can, which is ambiguous between a count noun and auxiliary, right? We can see in the lattice there's going to be a sequence of elements that correspond to the shared distribution between can and may. They're going to correspond to things like auxiliaries and count nouns. So the maximal elements of this are going to correspond in a sense to latent structure in the annotations of the parse tree. So we're going to choose the maxima. And if we have this sort of maximally labeled tree, in our semi-ring we have natural residuation operations, and it's going to satisfy these residuation operations at every point, that this residuation property. So we're thinking about syntactic structure. Okay. We have, I think, a pretty good argument that the labels should correspond to these closed sets of strings, these elements of this semi-ring. And we're interested in having these maximally labeled elements of this. The question is, what should the structure of the tree be? If we fix the structure, then we have some well-defined labelings. But what should the structure be? Now, we're considering all the images of all possible parse trees and all possible context-free grammars. So we're clearly going to have two degenerate cases. One degenerate case is where our parse tree is going to be too shallow, like this. We'll always have something which has no structure but just a list like this. We're also going to have ones which are too deep, where we have this sort of structure. Okay, both of these are wrong, right? We want to factor these out. Now, if we think about this kind of situation here, we have, it's clearly redundant, right? If we have a local tree that looks like this, this doesn't really contribute anything, right? Because the set of strings at the father of this is exactly equal to the set of strings at the child, right? This is redundant. We can also have exactly the same type of redundancy in a binary rule, right? In a binary rule, we'll always have that this set X contains the concatenation of Y and Z. But if X is exactly equal to Y and Z, in a sense, this is also redundant. Okay? So what we're going to do is say we want these trees which are maximally labeled, that have no redundant subtrees, and are also as deep as possible without being redundant. Okay, so we'll rule out the degenerate case where you just have a depth 1 subtree by saying, well, this could be deeper. So we want it to be as deep as possible, but without being too deep. Okay, this now gives us, for every context-free language and for every string, a notion of syntactic structure. Let me just give you a few brief artificial examples.
I'm sorry, I'm so confused why this would give you a unique tree. So this So
it doesn't give you a unique tree. It gives you a well-defined set of trees for each thing. So we'll see an example where we have some ambiguity in a bit, because obviously we don't actually want a unique tree for each thing, because natural languages are syntactically ambiguous, and we potentially want to have more than one tree for a particular string. So let's take a case of a language like the Dyke language, the matching bracket language, where we're going to replace open brackets with A and closed brackets with B. In this sort of trivial example here, we end up with a unique tree which looks like this. Okay. If we have the classic example of A to the n, B to the n, we end up with a unique tree that looks like this. Okay. If we take the Safran, Aslan, and Newport data where they have trisyllable of nonsense things, which is a classic example of distributional learning in infants, their test data, we run it through this approach and we get this sort of tree. And I'll just, if I, how much time do I have? 5 minutes? Okay. Okay, so, and I'll give a classic example from the linguistic literature of John is eager to please and John is easy to please. So this is maybe a little bit artificial because eager and easy, eager isn't a terribly common word, but the sort of, the point of this linguistic example is shown in something like this. We have John is ready to eat, the soup is ready to eat, and the chicken is ready to eat. Well, the chicken is ready to eat intuitively can mean either this delicious roast chicken is just come out of the oven, or it could mean, you know, it's feeding time for the chickens and they're running around pecking or whatever. So what we want to do here is we want to say, well, okay, this, these two are unambiguous, and this one is ambiguous. And we want, in some sense, to be able to recover this just from the surface sets of strings. So the methodology I did is I wrote a little toy grammar. I learnt the context-free grammar from examples, and then I used this algorithm to derive the set of all possible valid trees. So what you get is, you get something that's maybe not exactly what one wants, but this is what we got. We had, for the sentence John is eager to die, we get two distinct tree structures that look like this. For the soup is ready to eat, we just get one tree structure like that. And for the chicken is ready to eat, we get three tree structures. And if we compare the three tree structures, we see that one of the tree structures, the chicken is ready to eat, looks exactly like the soup is ready to eat, and the other two look exactly the same as here. The chicken is ready to eat, John is eager to die, the chicken is ready to eat, John is eager to die. So we don't get exactly the one-to-one mapping between interpretations and trees that we might like, but we're learning the fact that a sentence is ambiguous purely from a set of strings without any annotations. Now, context-free grammars are clearly not adequate to represent all of the things that happen in natural language. So typically one has movement. So in a classic linguistic case, what you'll do is you'll have a sentence like, what did you eat? And the what is considered to having moved from the object position of the VP up to here. Apologies if there are any real linguists here, because it's a bit of a Frankenstein's monster here, mixing several different notations. So what we're thinking really here is that we have some substring, a point in the construction here where we have eat and what, and this is going to be mapped into a discontinuous string in the surface. We can do exactly the same thing here. Actually, we can do exactly the same thing here with, take the same thing, where rather than having just a power set of individual strings, we have a power set of tuples of strings. This gives us a multi-sorted algebra, and then the homomorphisms would correspond to morphisms of multiple context-free grammars, or equivalently of tags, tree-adjoining grammars. Okay, so we can make some kind of linguistic predictions here. So if we have a word you, we can think of the lexical entries for you as being lex of u, and we can consider CL of u to be the distribution of the set of strings. Now clearly, if we have two words that have exactly the same lexical entries, then their distribution in the language is going to be identical. What we can say now is that maybe we can predict that this is going to be, the reverse is going to be true, that if two words have exactly the same distribution, then we will say they have to have the same set of lexical items. Okay, so we can make, using this sort of technique, if these structures are the right sort of structures, then we would expect these sorts of predictions to be true. Okay, so let me conclude now. Okay, so the standard view is your structure in a language is going to be given by some grammar. Okay, and this, in a sense, leads to an ill-posed learning problem. But the view I'm putting forward here is that we can view syntactic structure as being something that's inherent in the data. Okay, it's a sort of empiricist structure. So what we're saying is that languages themselves have an intrinsic hierarchical structure. That using these sort of mathematical tools here, we can derive a mathematically precise notion of structure. But how on earth do we want to evaluate that? So conclusion. So I think there's an interesting commonality between distributional learning and simplicity-based learning, which we can see through this machinery of mapping context-free grammars through homomorphisms. And the syntactic category should be elements of this sort of canonical representation, right? This lattice structure, the semi-ring structure, provides, if you like, a vocabulary in which we can write context-free grammars in. And then we can define a notion of syntactic structure using a set of simple local conditions on trees, that they're maximally labeled, that all the local trees are non-redundant, and that there's no substructure. Okay, I'd just like to thank some people who have made comments on some of this work, Hans Liss and Ryo Yoshinaka. Thank you. Yeah.
So as far as I can tell, there are 3 steps for finding a CFG here. First one is finding an initial CIS that works for your set of strings, finding the unique minimum CIS, and then finding a CFG that works good with that CIS. Am I right?
Yeah, that's
approximately
yes.
Something like
Yeah,
that.
yeah.
I don't know. Maybe I'm kind of off base, but yeah. Okay, what part of it do you think is the one that's really that's hardest to compute?
Okay, so that's a good question. What I'd say is all of those steps are really, really hard to compute, but you don't need to compute them, right? What you can do is you can go directly to the, let me see if I can find the right. Okay, it's, so like, I think what you say is, right, you have, you started from G, you go to here, and then you kind of go to here. Which of these steps is hardest, right? What I'm saying is you don't do that. What you can do is you can go straight for this, right? Because the elements of this are closed sets of strings, which one can infer directly from observing the relationship between non-terminals and between substrings and contexts in a language, right? So if you take some finite sample of data, you can observe the relationship between some of the contexts and substrings, right? And the elements of here, the non-terminals you want, will lie in that set. Right? So I think rather than starting from some arbitrary context-free grammar, which is the way I phrased it, I think algorithmically one will want to just go directly target this. So rather than doing a Bayesian thing where you're searching for, you may be doing some stochastic search through something, what one can say is, well, we know that the map solutions will have elements in there, so you can just directly search for those.
And that's the minimum CIS right there?
This is the, well, okay, sorry. There's a slight term. So this is the minimum CIS, right? When you map it into, you can find elements of this. You know that the minimal grammar is going to have elements in here, so then you have to identify some subset of these things that you're going to use as non-terminals. But you know that your non-terminals you want are going to lie somewhere in this algebraic structure, so you can restrict your search space if you're interested in these minimal solutions. There's some more computational stuff to do that. I'm simplifying a little bit.
I was wondering if you could relate this view of things to a pair of views of category. So in one direction, you can ask of a non-terminal, what does it derive?
Mm-hmm.
The other direction, you can ask of it, what derives it. So you can ask in what context do things of this category arise. You can ask what elements does this category of things thinking about what might make a natural category, and somehow what you're doing is related to these, and you don't know how.
Okay, so what we're mapping here is we're saying for each non-terminal here, we're going to map it to the set of strings that's derived from it. Alternatively, what you could do is you could say, well, let's take the set of contexts such that we can derive S. So take context LR such that we can S will derive LNR. And we can look at the sets of strings that occur in all those contexts. Now, if you do that, you don't get the universal property because it's not. If you map it in that way, you don't always end up with a grammar that has the right properties. Yeah, so in this case, you definitely want to map to this rather than the set of strings that can occur in all the contexts that the non-terminal can occur in. Now, there's an interesting open question whether you can transform every grammar, a context-free grammar, into a grammar such that that set of strings and this set of strings coincide. And I think I don't know whether you can or not. So for some context-free grammars have the property that if you take the set of contexts, you take the set of strings that can occur in those contexts, that will coincide with the set of strings that can be derived from that non-terminal. You can certainly do that for all regular languages, but I don't think you can do it for all context-free languages. I don't know if that...
This is a fairly basic question, but so if I wanted to put it to actually, so you implemented something like this for,
Yes.
for examples and for various purposes. I think what I'm not, perhaps it's just I missed it, but how do I first identify the language in the first place? So if I actually want to do natural language learning, and you're telling me I just want to find the CFG that generates the language, and there's of course a lot number of CFGs, and now we have a very clean way of identifying a particular CFG that matches a lot of sort of seeming natural construction. But I guess the question is, how would I describe that language if I had, say, tree bank or a crawl from Google, I would say maybe the language is self-respecting this.
Yep.
But this I think comes back maybe to the point about Bayesian learning. I guess in a sense you can use probabilistic algorithms as perhaps doing a kind of minimum risk where I try to maximize the probability of the truth that I observe, but I also reserve some probability of the truth that I observe. So I guess the question is when I want to count for strings I don't observe in the language.
Okay, so what I described really here is I've been assuming that you can do the weak learning, and the question is how do you go from weak learning to strong learning? And so for weak learning, there are algorithms I've been developing using distributional learning. There are other approaches, or in some cases, one might think, well, actually the underlying language is in fact regular, right? In which case one might be able to infer some regular language and then nonetheless derive hierarchical approximation. So, for example, the toy example I gave at the end, actually, I think it even defines it's actually a finite language. So, in which case, the weak learning problem is in principle trivial because you could just memorize it. The question is, how do you go from that representation, which is just in that case maybe just a list of strings that doesn't tell you anything, to a representation will tell you that some strings are ambiguous and some strings are not. So the weak learning, I mean, I've been doing a lot of work on weak learning over the last few years, so there are a number of theoretically well-motivated algorithms for learning, albeit under slightly unrealistic assumptions. So what this is meant to do is to go from a weak learning result, which is technically interesting but linguistically uninteresting, to a result here where we actually are starting to make some more linguistic predictions. Yeah.
You also did argue that the weak learning
I think weak learning. I think the thing weak learning is quite well defined. I mean, there's at least mathematically. I think in the what I'm trying to do here is to put strong learning, if you like, to make that as well defined as weak learning is, albeit by restricting the set of structures according to these criteria.
Fine, but you're already learning according to someone's theory who annotated the paper and you do the weak learning.
No. So in weak learning, I've been learning not from annotated. The weak learning here, I assume you're learning. So most of the algorithms I've developed so far either work just on strings, or on strings where you can also, and the unrealistic assumption is that you can also query whether a string is in the language or not. So that's when I said it was an unrealistic learning model. The idea is you're given a sequence of examples. In addition to those sequence of examples, you can also say, okay, here's a string I've made up. Is this grammatical or not? So that's clearly an unrealistic assumption, but it's okay. Yeah.
Part of this system where you choose what context you consider, you made the transition from what you're proposing now to the distributional learning just a little bit fast.
Yeah, so in these distributional, there are a number of different types of distributional learning algorithms, but typically they all work in the same way, in that you maintain a finite set of contexts and a finite set of strings. And depending on exactly on how the algorithm works, either you occasionally increase the set of strings in order to increase the size of your hypothesis, or you increase the set of contexts in order to decrease it. So typically you maintain two sets, one of which will tend to increase the language you generate and one of which will decrease it. And then by trading off these two, you can converge to something that's exactly right in a polynomial amount of time. So the exact details of that depends on the exact type of learning result you have and the sort of learning algorithm and so on. But yeah, so typically and if you're doing a more practical probabilistic one, you're going to restrict yourselves to contexts that occur quite frequently in the corpus, and similarly to substrings that occur frequently in the corpus, so that you can then observe the stochastic relationship between them reasonably efficiently.